Hey friends, welcome to the YouTube channel all about electronics. So in the earlier videos of the electromagnetic theory, we understood about the vector algebra. So now in this video and in the upcoming videos, we will learn about the different coordinate systems. So the first question that comes to in our mind is like, what is the point of learning these different coordinate systems in the electromagnetic theory, right? So the reason is that if you see the real world examples in the electromagnetics, then the different objects have the certain symmetry. For example, if you take the case of the parallel plate capacitors or the circuit board traces, then they have the planar symmetry. So while dealing with such objects, it is easy to define the electric and the magnetic fields in the Cartesian coordinate. And in fact, it also becomes easy to solve the Maxwell equations as well as the boundary conditions in the Cartesian coordinate. But on the other hand, if you see the coaxial cables or the long wires, then they have the axial symmetry. So for such objects, when we are defining the electric fields or solving the Maxwell equations, then it is easy to represent them in the cylindrical coordinate system. So when we define them in the suitable coordinate system, then what happens is that many variables can get eliminated. So because of that, the representation of the vectors as well as solving the Maxwell equation becomes easy. And the same is the case when we represent the point charge or dealing with the antennas because they have the spherical symmetry. So in such cases, it is better to represent the electric field in the spherical coordinate system. And suppose if the electric and the magnetic fields are not known in the suitable coordinate system, then we can also convert them in the suitable coordinate system. So along with the knowledge of the coordinate system, we should also know that how to convert the field vectors which is given in the one coordinate system into the another coordinate system. So if we know that, then based on the symmetry, sometimes very complex looking equations can be simplified to the very simple form. So during this video, we will see the cylindrical coordinate system and we will also learn that how to convert the vectors which is given in the one coordinate system into the another coordinate system. So as you are rightly imagining, this video will have the lot of mathematical expressions. But once we understand it clearly, then in the upcoming videos, it will become very easy to understand the different electromagnetic concepts. Alright, so now in the earlier videos, while discussing the vector algebra, we have already discussed the Cartesian coordinate system. So in the Cartesian coordinate system, if we have a some point P in the 3D space, then it can be defined by its three coordinates x, y and the z, where these x, y and z represents the distance of this point P from the origin in the respective direction. So similarly, we have also seen that how to represent the any vector in the Cartesian coordinate. So here, these ax, ay and the az are the unit vectors in the direction of x, y and the z. And likewise, these capital ax, ay and the az are the components of the vector in the x, y and the z direction respectively. Now if you see the unit vectors in the Cartesian coordinate, then the direction always remains fixed irrespective of the position of the vectors. That means even if the position of the vector changes, then also the direction of these unit vectors in the Cartesian coordinate always remains fixed. That means here the ax will always remain in this direction and likewise the ay and the az will always point in respective directions. But that is not the case in case of the cylindrical as well as the spherical coordinate system. So if you see the cylindrical and the spherical coordinate system, then they are the curvilinear coordinate system. But this Cartesian coordinate system is the rectilinear. That means if we keep the two axes constant and changes the another one, then you will move in the straight direction. For example, if we keep the x and z coordinates constant and changes the y coordinate, then we will move in the straight line. That means in this Cartesian coordinate, the direction of the unit vectors always remains fixed. But that is not the case in case of the cylindrical as well as the spherical coordinate system. So to understand that, first in this video, let us learn about this cylindrical coordinate system. So we know that in case of the Cartesian coordinate system, we have the three coordinates x, y and the z. So similarly, in the cylindrical coordinate system, we have the rho, phi and the z. So to understand what is this rho? Just imagine a cylinder that is centered around the z-axis. So this rho represents the radius of this cylinder. So in this cylindrical coordinate system, this rho can increase from 0 to infinity. So we can say that here the range of the rho is from 0 to infinity. So similarly, this phi represents the azimuth angle. So here, this azimuth angle 5 is the angle that is made by the radius with the x-axis. So here, this 5 can vary from 0 to 2 pi. So we can say that the range of the angle 5 is from 0 to 2 pi. And likewise, this z is the linear distance of the point from the xy plane. So similar to the Cartesian coordinate, this z can vary from the minus infinity to the plus infinity. That means here, the range of the z is from minus infinity to the plus infinity. So in this way, in this cylindrical coordinate system, we have the coordinates rho phi and the z. So now let's say there is some point P in the 3D space. And now, starting from the origin, if we draw a vector that is connecting this point P, then that will be the position vector in the 3D space. So in the cylindrical coordinate system, if we represent this vector A, then it can be represented like this, where the small arrow A phi and the AZ represents the unit vectors in the cylindrical coordinate system. And unlike the Cartesian coordinate, these unit vectors won't always point in the same direction, and rather their direction always depends on the position of the vector. So here, first of all, for the given point, let us find out the rho. So here, if we take the projection of this vector on the xy plane, then we will get this rho. And now, if I draw the imaginary cylinder that is passing through the z-axis, then this will be its radius. So here, this distance represents the rho. So now, let me also draw the line that is parallel to this radius. So here, if you see the direction of this unit vector a rho, then it will be in the incremental direction of the rho. So this a rho is known as the radial unit vector. So at a given point, it is pointing in this direction. But suppose if the point changes, then the direction of this a rho will also change. So similarly, now let us see the direction of the A5. So here, this angle represents the A5. And as you can see over here, this phi is increasing in this direction. That means here, this unit vector A5 will also point in the direction in which this phi angle is increasing. So that will be in this direction. And if you see its direction, then it is tangent to the cylinder. And therefore, sometimes this vector is also known as the tangential vector. And likewise, the direction of the unit vector AZ will be parallel to the z-axis. So at this point, if you see, then this arrow A phi and the AZ are orthogonal to each other. That means here, all the three unit vectors are perpendicular to each other. So because of that, if we take the dot product of any two unit vectors, then that will be equal to 0. Because in the earlier video of the dot product, we have seen that if the two unit vectors, or in general if the two vectors are orthogonal to each other, then the dot product will remain 0. That means here, if we perform the arrow dot a5 or the a5 dot az, then that will be remain 0. And likewise, this az dot arrow will also be equal to 0. But on the other hand, if we perform the dot product with the unit vector itself, then that will be always 1. That means in this case, this arrow dot arrow will be 1, and likewise, this a5 dot a5 and the az dot az will also be equal to 1. That means the dot product of the unit vector with itself will be equal to 1. And likewise, if we perform the cross product between the two unit vectors in the cyclic order, then we will get the another unit vector. For example, if we perform the cross product between the arrow and the a5, then we will get the az. So likewise, if we perform the a5 cross az, then we will get the arrow. And similarly, this az cross arrow will gives us the a5. So that is all about the unit vectors in the cylindrical coordinate system. So similarly, if you see this arrow a5 and the az, then they are the components of the unit vector in the respective directions. So very soon we shall see that how to find these components. But before that, first let us see if we have been given a one point in the cylindrical coordinate system, then how to convert it into the Cartesian coordinate system. And vice versa, we will also see that if the point is given in the Cartesian coordinate system, then how to convert it into the cylindrical coordinate system, because this conversion will be required for finding this arrow Fi and the Az. So to find that, first let us project this point on the xy plane. So here, this distance will be the z. So in this way, we will get our z coordinate. So as you can see over here, in both coordinate systems, the z component remains the same. So now, let us connect this point with the origin. So this distance represents the rho. And now, the angle that is made by this line with the x-axis represents the azimuth angle, that is equal to 5. So if we take the projection of this rho on the x-axis, then we will get the x component. So we can say that here the x is equal to rho cos 5. And likewise, if we take the projection on the y-axis, then we will get the y component, that is equal to rho sin 5. So from this we can say that here this x is equal to rho cos 5 while the y is equal to rho sin 5. So in this way, for any given point, if we have been given the coordinates in the cylindrical coordinate system, then using this formula, we can convert it into the Cartesian coordinate system. So similarly, now let us see the other way around and let us find out, suppose we have been given a point in the Cartesian coordinate system, then how to convert that point in the cylindrical coordinate system. So we already know this relationship, right? That means here, during the Cartesian to cylindrical conversion also, the z component will remain the same. So now, to find this rho, let us do the x square plus y square. So here, if we perform the x square plus y square, then we will get this rho square cos square 5 plus rho square sin square 5. So if we take this rho square outside, then we will have this sin square 5 plus cos square 5, and that is equal to 1. So we can say that here this x square plus y square is equal to rho square, or we can say that this rho is equal to square root of x square plus y square. And similarly, from this relationship, if we take the ratio of y and x, then we will get the tan 5. So if we take the inverse, then this azimuth angle 5 can be given as tan inverse of y by x. So in this way, if we have been given a point in the 3D space in the Cartesian coordinate system, then using this relationship, we can find the corresponding cylindrical coordinates. And other way around, suppose we have been given the coordinates in the cylindrical coordinate system, then using this relationship, we can find the corresponding Cartesian coordinates. So now, once we know this coordinate conversion from the Cartesian to cylindrical as well as the cylindrical to Cartesian coordinate, then the next important thing which we should know is the vector conversion. That means suppose if we have been given the vector in the Cartesian coordinate, then how to convert it into the cylindrical coordinates, and vice versa. Suppose we have the vector in the cylindrical coordinates, then how to convert it back into the Cartesian coordinates. So here, instead of directly applying the straightforward transformation, we will derive those expressions so that you have the better understanding about the process. So as a first step, what we will do, we will find the unit vector transformation, and we will see that how to convert the unit vectors from the Cartesian coordinates to the cylindrical coordinates, and then after we will see the other way around. So once we get that relation, then we will replace these unit vectors by that newly found expression, and with the help of it, we can find the relationship between the components ax, ay, az and the arrow fi and the az. So as a first step, let us see the unit vector conversion, and let us see how to convert the unit vectors from the Cartesian coordinates to the cylindrical coordinates. So for that, first let us take some point r in the Cartesian coordinate, and let's say the position vector which is connecting this point is equal to r. So this position vector can be written as this x times ax plus y times ay plus z times az. Because as you know, in the Cartesian coordinates, for the position vector, the components of the vector will be same as the coordinate values. So now, if you see over here, then what we need to find is the unit vectors in the direction of the rho, phi and the z. And if you see this expression, then it does not contain any variables such as rho, phi and the z. So here, what we will do, we will replace this x, y and z with their corresponding cylindrical coordinates. And here, we can do that because this x, y and z indeed corresponds to the coordinate values. So we know that here this x is equal to rho cos phi while the y is equal to rho sin phi and the z will remain as it is. So now if you see the expression of the position vector, then it is in the form of rho phi and the z. So now when we differentiate this vector with respect to the variable rho, then we will get the vector which is incrementing in the direction of the rho. And whenever we normalize it, then we will get the unit vector. So that vector is actually the a rho. So if you recall, then earlier for the cylindrical coordinates, we have seen that these unit vectors a rho, a phi and the az are pointing in the incremental direction of this rho, phi and the z. So that's why here this term will also corresponds to a rho. Likewise, if we differentiate this position vector r with respect to phi and normalize it, then we will get the unit vector a5. And likewise, we can also get the az. So now, first let us find this a rho. So to find this a rho, first let us differentiate this position vector with respect to rho. So here, if you see this del r by del rho, then that will be equal to cos phi times ax plus sin phi times ay. And here, since this term does not contain any rho variable, so that will become 0. And now, if we take its magnitude, then that will be equal to square root of cos square phi plus sin square phi, and that is equal to 1. So we can say that here this unit vector a rho is equal to cos phi times ax plus sin phi times ay. So in this way, here we got this unit vector a rho in terms of the ax, ay and the az. So similarly, now let us find the unit vector a5. So this a5 can be given as this del r divided by del phi divided by the magnitude of it. So here, if we differentiate this r with respect to phi, then we will get this minus rho times sin phi ax plus rho times this cos phi times ay. And once again, since the third term does not contain any variable phi, so it will become 0. So now, if we take its magnitude, then that will be equal to square root of rho square sin square phi plus rho square cos square phi. So here, if we take this rho square common, then we will have this sin square phi plus cos square phi. And as you know, that is equal to 1. So from this we can say that here this del r divided by del phi is equal to rho. And therefore, here this unit vector a5 is equal to minus sin phi times ax plus cos phi times ay. So similarly, now let us see the unit vector az. So once again, as per the definition, this az can be given as this del r divided by del z divided by its magnitude. So we know that in both cylindrical as well as the Cartesian coordinates, the z coordinate remains the same. So that's why this az should also remain the as it is. But here, let us also prove that. So here, this del r divided by del z will be equal to az, because if you see, then the first and the second term of this position vector does not contain any variable z. So that's why they will become 0. And for the third term, if we differentiate with respect to z, then we will get the az. And we know that the magnitude of the unit vector is same as the 1. So therefore, the az in the cylindrical coordinate system will be same as the Cartesian coordinate system. And in this way, we got the unit vectors a rho, a phi and az in terms of the ax, ay and the az. So similarly, now let us see the other way around and let us find out the unit vectors ax, ay and az in terms of the unit vectors a rho, a phi and the az. So here, since we already know this relationship, so we will find the unit vectors ax, ay and az with the help of the projection method. And in that, first we will find the unit vector Ax. So in general, this unit vector Ax can be expressed as the combination of these vectors a rho a phi and the az, where here the c rho c phi and the cz are the projection of these unit vectors a rho a phi and the az in the direction of the Ax. That means here this c rho is equal to this Ax dot a rho, and as you know, it is nothing but the projection of the vector a rho in the direction of the Ax. So here, since we already know the unit vector a rho in terms of the Ax and Ay, so we can easily perform this Ax dot a rho. So here, if we perform this Ax dot a rho, then we will get only this first term, because for the second term, this Ax dot ay will become 0. That means here, this Ax dot a rho is equal to cos 5. Likewise, this C5 is equal to Ax dot A5, and that is equal to minus sin 5. And similarly, this Cz is equal to Ax dot Az, and that is equal to 0. So from this we can say that this Ax is equal to this cos phi times a rho minus sin phi times a5. So in this way, we got this unit vector Ax in terms of the unit vectors a rho a phi and the az. So similarly, now let us find the unit vector ay. So once again, this unit vector ay can be expressed as the combination of these vectors a rho a phi and the az. So here, this c rho is equal to ay dot a rho, and in this case, that will be equal to sin phi. Likewise, if we perform this c5, then that is equal to ay dot a5, and in this case, that is equal to cos 5, and likewise this cz will be equal to 0. So we can say that here this ay is equal to sin phi times a rho plus cos phi times a5, and in this way we also found the relationship between the unit vector ay in terms of the a rho a phi and the az. So likewise, let us also see the az. So as we have seen, for the both coordinate system, the az remains the same. So based on this projection method also, we should get the same result. So as per this method, this az is equal to the combination of the unit vectors a rho a phi and the az. So here, this 0 will be equal to az dot a rho. And as you can see over here, as the a rho a5 does not contain any z component, so it will be equal to 0. That means here, this first coefficient is equal to 0, and likewise, this c5 will also be equal to 0. And then, if we see this cz, then that is equal to az dot az, and as you know, that is equal to 1. That means in this case, this az will be equal to az, and that is the expected result, right? So in this way, we got the Cartesian unit vectors in terms of the cylindrical unit vectors. And earlier, we already found the cylindrical unit vectors in terms of the Cartesian unit vectors. So now, with the help of it, we can find the transformation between the coefficients ax, ay and az and the a rho a phi and the az. So here, what we will do? First, we will find the relationship between the components ax, ay and az in terms of the a rho a phi and the az. So basically, here we will find the vector in the Cartesian coordinate from the cylindrical coordinates. That means here, we already know the vector in the cylindrical coordinates. So that is equal to a rho times a rho plus a5 times a5 plus az times az. So now in this expression, let us put the values of the a rho a phi and the az. So if we put the value, then we will get this expression. So if required, then you can pause the video and check this expression. So now from this expression, let us combine the terms which contains the unit vector ax. So if we combine that, then we will get this a rho times cos 5 minus a5 times sin 5. Similarly, let us combine the terms related to this ay. So if we do so, then we will get this a rho times sin 5 plus a5 times cos 5. And likewise, the last term will be equal to az. So now, if we compare this expression with the Cartesian vector, then the first term corresponds to ax. Likewise, the second term corresponds to ay, and the last term will be equal to az. So from this we can say that this ax is equal to this a rho times cos 5 minus a5 times sin 5. Likewise, this ay is equal to a rho times sin 5 plus a5 times cos 5, and this third term az will remain as it is. So in this way, we found the relationship between the components ax, ay and az in terms of the cylindrical components. And here, the same thing can also be written in the matrix form. So this is the transformation matrix for converting the vector that is given to us in the cylindrical coordinate to the Cartesian coordinate. So similarly, now let us see the other way around and let us find the Cartesian to cylindrical conversion. That means now the vector that is given to us is in the Cartesian coordinate. So now in this expression, let us put the values of the ax, ay and the az. So if we put the value, then we will get this expression. So once again, if required, then you can pause the video. So now from this expression, let us combine the terms related to a rho. So if we combine that, then we will get the term that is ax cos 5 plus ay sin 5. Similarly, let us combine the terms related to a5. So if we combine those terms, then we will get minus ax times sin 5 plus ay times cos 5. And likewise, the third term will remain as it is. So now, let us compare this expression with the vector expression that we want to find in the cylindrical coordinate system. That means here, this term corresponds to a rho, and likewise, this term corresponds to a5. So from this we can say that over here, this a rho is equal to ax cos 5 plus ay sin 5, and likewise this a5 is equal to minus ax sin 5 plus ay cos 5, and the az will remain as it is. So in this way, we also found the cylindrical vector components a rho, a5 and az in terms of the Cartesian coordinates. And the same thing can also be written in the matrix form. So now, if you compare this matrix with the cylindrical to the Cartesian conversion matrix, then we can find that by just taking the transpose of the given matrix. And vice versa, it is also possible. That means here, we just need to remember only one transformation matrix, and from that, we can easily write the another one. So with the help of this transformation matrix, we can convert the vector from the cylindrical to the Cartesian coordinates as well as from the Cartesian to the cylindrical coordinates. So earlier, if you recall, then for the simplicity of the derivation, we have assumed that the given vector is the position vector, and we have assumed that the point in the Cartesian coordinate is equal to x, y and z. So the corresponding position vector was x times ax plus y times ay plus z times az. That means in case of the Cartesian coordinate, if we have the position vector, then the components of the unit vectors are same as the coordinate values. But that is not the case in case of the cylindrical coordinate system. So now, with the help of the transformation matrix, let us see what will be the expression of the given vector in the cylindrical coordinates. So we know that the vector components in the cylindrical coordinate system can be represented like this. So here, if you see this a rho, then that is equal to ax cos 5 plus ay sin 5. So in this case, this ax is equal to x while the ay is equal to y. And moreover, we also know that this x is equal to rho cos 5 while the y is equal to rho sin 5. So if we put the values of x and y, then we will get this rho times cos square 5 plus rho times sin square 5. And as you know, this cos square 5 plus sin square 5 is equal to 1. So we can say that this a rho is equal to rho. So similarly, let us find the a5. So as per this transformation matrix, this a5 can be given as minus ax sin 5 plus ay cos 5. So once again, if you put the values of the ax and ay, then this a5 expression can be written as minus x sin 5 plus y cos 5. So once again we know that here this x is equal to rho cos 5 while the y is equal to rho sin 5. So if we put these values, then this a5 will be equal to minus rho times cos 5 times sin 5 plus rho times sin 5 times cos 5. So as you can see over here, both these terms will get cancelled out and therefore this a5 will come out as 0. So in this way, we also got the second term. And as you can see, this az will be same as az. So in this way, we got all the components. And from this we can say that this vector A is equal to rho times a rho plus z times az. So in this way, with the help of this transformation matrix, we can convert the any vector that is given to us in the Cartesian coordinate to the cylindrical coordinate. And if we take the transpose of this matrix, then we will get the relationship between the ax, ay and az in terms of the a rho, a phi and az. So in this way, in this video, we learned about the cylindrical coordinate system and we understood that how to convert the point that is given to us in the Cartesian coordinate to the cylindrical coordinates. And we have also seen the other way around. And then after, we also understood the vector conversion between the two coordinate system. So in the next video, similarly, we will learn about the spherical coordinate system and we will also see the vector conversion between the Cartesian and the spherical coordinate system. So if you have any question or suggestion, then do let me know here in the comment section below. If you like this video, hit the like button and subscribe to the channel for more such videos.